in the figure contains water at 20 degrees Celsius. Right? And it is being filled through section 1. This is our section 1 here. And we are told to assume incompressible flow. Just hang on a second. Continuing, it says to first derive an analytic expression for the water level change dH dt in terms of the arbitrary volume flows Q1, Q2, Q2, and Q3, and tank diameter D. Then, if the water level H is constant, determine the exit velocity V2 for the given data. V1 is about 3 meters per second, and Q3, this is 0.01 cubic meters per second. So this is the volumetric flow. Right, and right, so when it comes to mass conservation, your first step always is to draw your control volume, which gives you an idea of what's happening in your system. So our control volume here will right, so everything, the fluid getting into the tank, right, so the control volume will essentially correspond to these vertical walls and this horizontal one here. And so for the equations for that, we'll consider, right, so let's first write our knowns. Right, so this is the temperature of water, which is at 20 degrees Celsius. So this here can help you get the density. Let's consider our control volume, our mass flow equation. So we'll essentially consider everything going into the control volume as well as everything going outside of it. So quite simply, let's consider d dt of the integral of rho dv Right, so this is density multiplied by volume, the differential volume to give us mass, and plus. So let's consider a rho, and then yeah, since this is going inside the tank, right, and this here will take Q2, the volumetric flow rate, and then subtract the Q1 and that Q3. And this is going to be equal to 0. And since we're told that this is incompressible here, we can take out the density. So what you need to understand by that is that for incompressible flow, rho is constant, which means that in your integral, you treat that as a constant value. So this is d dt of integral dv, and this is equal to let's take it as minus rho q, rather let's consider rho q3 plus q1 minus q2. This is rho d dt. When it comes to our volume here, we'll consider the area, and we want to multiply that by volume. Just, so this is our differential volume here. Area multiplied by velocity, which is going to correspond to so the area that's going to correspond to, consider the density, and then just a minute. Let's see if, okay, it's actually going to be area multiplied by our water level h here instead of velocity. Just always make sure you have that right. So what we're going to be looking at here is area multiplied by h, which is rho q3 plus q1 minus q2. And the densities cancel each other out. And when you apply the product rule to this here, what you're going to end up with is A multiplied by dH dt is equal to Q1 plus Q3 minus Q2. And then our area, we're going to base it on density, on our diameter. So this is Q1 plus Q3 minus Q2 divided by pi by 4 d squared, as I've shown you before, how this comes to be. Does anybody have any questions here? Anybody questions? All right, no questions. So what we were given was that all right, so essentially what's going to happen here is that if our water level h is constant, that means that the derivative dh dt is going to be equal to 0. That's a constant value, derivative of a constant. And from there, we want to determine the exit velocity v2 for that given data. So if we have v1 and q3, from v1, right, we can work out what q1 is, because that's simply going to be area multiplied by volume, right? So this is the volumetric flow rate, while the other volume that is given by area multiplied by h. So take note of that distinction. And with V1, with Q1, we do have V1, and we can work out what E1 is. So if our dH dt is equal to 0, that means that we can take this term, multiply it to the left side, and that is going to leave us with Q1 plus Q3 is equal to Q2. And what we're looking for here is V2, the exit velocity. So that means that this is pi by 4. Diameter at 2, that is 0.07 meters multiplied by V2. And Q1, that was given as, that wasn't given, so but we can work it out nonetheless. 3 pi by 4, and that's 0.05 all squared. The value of Q1 that was given as 0.01. And from there, you can work out what V2 is. Right, so just quickly work that out on you, and as well, let me know what you get. The answer I'm getting here is that V2 is 4.1291 meters per second. Right, so our analytic expression here for dH dt was given by that. And we're now going to be looking at question 2. So in preparation for the test, what I recommend here is that just go through everything that we went over, and then with every tutorial question, make sure that you understand it in detail, like you understand the reasoning for the logic behind each step, the rationale. Just does anybody have any questions here? Can we move on? Uh, just 1 second.
You're muted.
Just 1 second. All right, so what I think you might struggle with here for this question is that when it comes to breaking down this equation and getting it to here, I didn't show how you can go from the conservation of mass equation. Right, so for a fixed control volume, this is how your equation looks like. And what normally happens, like with the equation we have above, is that we're looking at d dt of the integral cv rho dv plus rho v dotted with n dA that's equal to 0. So you saw how we solved that, right? So that's perfectly fine. And then when it comes to this equation here, right, it's a one-dimensional inlet as well as outlet we're considering, right? So the velocities here, those are constant, so meaning that when you now consider the area, the the, um, the integral of that is simply going to be a. So what you're looking at here is v dotted with n dA. What follows from that? A. And that is equal to 0, right? Which is, you also saw that variable on the density. So this density there, that was the same density present here. V multiplied by A. So remember that this gives you direction, nothing more. and we've looked at that before. So V dotted with N, that is greater than 0 for an outlet. But V dotted with N, that is less than 0 for an inlet. You can refer back to the video for that, for the in-depth explanation. So this is nothing more than direction. So that means that what we're looking at is rho Q, volumetric flow, which is made up of V multiplied by A. While the Q here takes into account the direction due to V dotted with N. So once you simplify that, that is going to be d dt rho C plus rho. And then for our inlet here, the two inlets, these are going to be negative while the outlet is positive, just like you can see here. So this is positive Q2 minus Q1 minus Q3, that is equal to 0. So this is where you start from, right, for conservation of masses here, and then you simplify that equation, well, here. Is everybody happy with that? All right. Perfect. Let's now move on to the next question. All right. We're given that a thin layer of liquid draining from an inclined plane as a velocity V is equal to V naught multiplied by 2r divided by h minus y squared divided by h squared, where V naught, this is the surface velocity. If the plane has a width 10 centimeters into the paper, determine the volumetric rate of flow in the film. Suppose that h is equal to 2 centimeters and that the flow rate is 2 liters per minute. So what we're given here, what we're looking for is Q. And what we have is dV dt. That's what the 2 liters per minute gives us. That's volume over time. Right, and right, so the velocity profile so imagine you have some inclined plane, right, to give you an example of how you might consider looking at this. Your inclined plane is like that. It may be a plank, and from it, you put a water hose here. Does that example make sense? So that's where you have your pipe and the water is flowing out. Right, the velocity profile that we're looking at here, it gives us the behavior of the fluid relative to that inclined plane. Right, so let's consider our volumetric flow equation. Right, this is given by V is equal to so our velocity multiplied by area. So what we have here is the velocity profile and area. Given that we have a width of the plane as well as the h, given the height value h. So what we can do here is to consider q given as our volumetric flow multiplied by the differential area. So to get q over that entire plane, that will be v multiplied by our differential area. And v here is given as v naught 2y divided by h minus h squared divided by h squared, like that. Now multiplied by. So when it comes to our differential area here, we can write that as so let's consider the width, which is 10. Right, so the width, they will just call it W.
The term is y squared over h squared. You wrote h squared over h squared.
I could catch on that. Thank you. So this is y squared. So we'll just call that W. And then the height here, h. Let's consider. So for the area, we'll consider the width, right? And we'll multiply that by the differential length dy. In that manner. So here in the example, given that h here is equal to a certain value, but we're not interested in looking at h at this point. Want to look at that small change in length. So once we consider that small change, think of that in 3 dimensions. We have dy here, and then it's also going to extend into the page. So something of that sort. You have that width that we're talking about. So this is, well, this dy, and here we have w, that width, which is going into the page in that manner. So when we compute that area, that is going to be its differential area made up of w and dy. Okay. So for w, you're going to sub in the actual value, which we can take out of the integral. That was 0.01 0.1 integral v naught 2y divided by h minus y squared divided by h squared dy. And from there, we want to integrate this from y is equal to 0, and then finally where y is equal to h to give us our q. So we essentially want the differential, the volumetric flow over that entire page. And there is our expression. The second question here says that suppose, so this is the volumetric flow that we determined. For this here, you expected to work out what the integral, what q is going to be. So integrate that. That should be easy enough to do. And now with us given an h of 2 centimeters here, and our volumetric flow rate is 2 liters per minute. This is cubic meters per second, right? So which means that this here actually represents you. This is your Q. That is your Q there. Your dV dt. That is what gives you Q. You can just sub in these values once you have them. Because here, if you solve for H, and this is your unknown, this is your known now, and this is your only unknown, you can solve for it. Does everybody understand? All right, perfect. So for part one of the question, essentially going to say that you're looking at this integral here, and you solve for it to get a Q expression. So Q is equal to 0.1 V naught integral from 0 to H 2y divided by H minus y squared divided by H squared. So the H variables here are treated as constants. So meaning that if you want to integrate that, yeah, it will be 2y divided by simply 1. So H integral 2y dy from 0 to H. So that's how you will do your integration. So you're going to come up with an expression for that in terms of V naught and H. So Q given as a function of V naught and H. And the second question here gives you this value, this Q, and you want to work out what V naught is given an H of 2 centimeters. So with your units, you always have to make sure that they are consistent, meaning that you will convert this to cubic meters per second. But if you struggle with any of that, you can let me know. And then our next question here says that compute the volume flow Q across the top surface of the control volume. But the plate has width B into the page, into the paper. Oh, just hang on. This goes on top and this beneath. Just hang on. All right, so for our last question here, it says that an incompressible fluid, you know what that means now. It flows past a flat plate as shown in the figure. So this is your flat plate here. Right, and it has a uniform inlet profile and a just a second. All right, so we have an inlet profile and a polynomial exit profile with Vx, this being the velocity along the x direction, being equal to V naught multiplied by 3 eta minus n cubed divided by 2. And that's where our eta here is equal to y divided by delta here, which is the boundary layer thickness. And that is not something that we've done together yet. The V naught here implies that Vx is dependent on this constant velocity. Constant velocity there. So here, I want to work out what's the actual question, just now. What are we being asked to do here? All right, so I want to compute the volume flow Q across the top surface of the control volume. The pleat has width B into the paper. So what's going to happen here is that if we consider the mass conservation equation, there's no mention of time here, which means that we can let the time associated terms go to 0. This here, there's no mention of any kind of time, right? And what we're looking for is Q across the top surface of the control volume, right? And what we note here from this equation, as we've shown before, this is simply going to reduce to rho sum of Q. This is equal to 0. This being the volumetric flow. Since Q is the only is a constant term, we can just divide by it. So we'll consider this is going to be minus since it's going in, it's into the pipe or the system, into the control volume. And this here, that is going to be positive. So this is Q1, Q2, and this here, we can leave it as Q. Right, so what we have is Q2 plus Q. This is equal to Q1. Q1, this is equal to Q2. For Q2, we're looking at a parabolic velocity flow. So we'll take the velocity, we'll multiply that by area. So this is V multiplied by. So these terms here you don't have, well, the eta, what this means here, the delta, you don't have to worry about that for now. So this is going to be just a second. Can everybody still hear me? All right, perfect. So the way we're going to set up our Q2, there's a Q, yeah, this Q here, we're taking that velocity, that parabolic velocity profile, which is given by, well, that V naught, right, multiplied by this here, which is velocity. So this is our Vx multiplied by, well, area to give us Q2. That's what we rely on. So we take that Vx and the area here. So since this profile is parabolic as well, it's not linear. When you calculate area, it's not simply going to be the length multiplied by the height. We have to consider the differentials. So we'll consider the width B as well as the differential vertical length dy for that profile. So this is V dy. And then for Q, all right, so for Q, we're going to keep that as is because that's actually what we're looking for. And then for Q1, we'll take the V naught and then we'll use the same formulation as well, by considering that change in dy as well. So this is going to occur independently of the kind of profile you're looking at, but simply because of the fact that we want to use it across that entire page. So this is going to be V naught multiplied by B dy. And this is V naught 3. So in the place of eta, we have y minus y cubed divided by delta cubed. This is B dy plus q. And from there, you can solve for q. Right, the delta here is a constant value. So you do not need to worry about that. You can treat it as a, well, exactly what's going to happen is that when it comes to y, you'll go from y is equal to 0 to y is equal to q, up to delta, this delta here, when you're now evaluating the integrals. Does that make sense? All right, perfect. Any questions on these tutorial problems?
I have a question, but it's not in the tutorials. So he was going through like the cuts during class, and he gave us an extra question. Can I send it in the group now and then ask?
Yeah, you can send it through and then I'll give you feedback right after the meeting.